Sure. Let me get set up for a second. You mean where those force equations come? Okay. So the perpendicular force, this is the sum of, this is the sum of the forces, in particular direction. Okay. Mhm. Oh, okay, okay. Where do you find this? So I think, okay, so I think what they're doing. Really contact schedule, off schedule. So I think what they're doing is that, so by inline, they're basically summing the forces in every direction in line with the arm itself. So they're doing a sum of forces, but doing it in any direction, it's not the x direction. So, so you can do that, that is possible. But but I think an easier way to do it is with the sum of the forces all in x direction, and the sum of the forces all. So I will give you jx and jy direct. But they kind of did like an extra step, summed up all the forces in this direction, and then they did some trigonometry. And then they summed up all the forces in the perpendicular this direction here. And then they did some trigonometry to basically take those two components and then basically transform that into like x direction as well. Here. But you can try to do it all in one step. You just sum the forces in this direction, because then that equation would just have x. If you sum the forces in the one direction, then you just get a force. Yeah, so it's a sum of forces, but they just did kind of two weird. We'll go over this a bit today. So this is one thing that you can do. But if you're just searching for joints and data line, I think it's easier to just sum the forces in the correct direction, something like that. Yeah. Okay, it's 4 o'clock. Let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. Weather is good. I feel like I'm getting old because I feel like I have to comment on the weather every time I see, not just you guys, but it's just people in general. I feel like I have to comment on the weather because I feel like it's getting harder for me to connect with people maybe. Okay, so the plan for today is we're going to finish up our lecture notes on upper extremity biomechanics. And so I have a couple more examples to kind of show for you guys. So all of last class, we mostly focused on just the biceps muscle and the elbow. Today we're going to move a little bit further up. So we're going to go up to the shoulder, look at the deltoid muscle and kind of see what that's all about. Okay. I think one particular example I think will be useful for today, for those of you who are working on the homework. One of the examples that we'll show today is the arm kind of positioned at a lower angle. And so we're going to see how that affects your calculations and how I generally approach those types of problems. Okay. After that, we'll finish up our upper extremity notes. We'll talk a bit about just some common injuries that can occur in the upper extremity. And then just with whatever time we have left today, we'll go ahead and move on to the lower extremity. Okay. All right. Any questions I can answer before we get started for today? Okay. All right, so let's go ahead and pick up where we left off. Okay. So we've kind of last week we kind of started this journey into kind of this bigger unit, which I call kind of static biomechanics. Okay. And so the whole idea with static biomechanics is that we're going to be analyzing different parts of the body in static configurations. And the whole idea is that we're going to be analyzing different positions in static equilibrium. Okay. And remember, the whole idea with static equilibrium is that there's no motion, so there's no velocity, no acceleration, or anything like that. And so when we sum up all the forces, we sum up all the moments in our problems, all of those are going to sum up to 0. Okay. So that's kind of the general theme of last week, as well as probably the next 2.5 weeks, is that we're going to be doing a lot of free body diagrams, a lot of force summations, moment summations, and it's all going to be equal to 0. Okay, and what that's going to give us, okay, generally for 2D problems, we're going to have 2 force equations and 1 moment equation. Okay. Okay, so our 2 force equations are the sum of the forces in the x direction and sum of the forces in the y direction. Okay. And then we're also going to have 1 moment equation. Okay. And technically that moment equation, remember when we sum up moments, the direction of the moment equation is always in the perpendicular direction, right? And so we're technically summing up the moments in the z direction because the axis of rotation is in the z, coming out of the page piece. Okay? So that gives us 3 equations that we can play with. And generally what this means is that we can solve for 3 unknowns or 3 unknown variables in our problems. Okay? And generally the 3 unknown variables, number 1 is always going to be the muscle force. Okay? Usually we denote that as FM. And so in all these problems, there's going to be some muscle force that's unknown. And so we want to solve for how much muscle force is needed to maintain this position. Okay? And number 2 and 3 kind of belong to the same category. They're just 2 different components of the same thing. And those are the joint reaction forces. Okay. So typically, just the way that just because of the way I sum the forces, typically the joint reaction forces will be in the x direction and the y direction. Okay, so we have Jx and Jy. But actually, the only requirement for the joint reaction forces are that they're acting kind of in perpendicular directions, right? So I think the most classical way is to do one in the x direction and one in the y direction. That's kind of the classical kind of orthogonal Cartesian vectors. But sometimes it may be useful to have a force vector that's parallel to whatever body segment that you're looking at and perpendicular to. Okay, so we're going to do one example for that today, right? So typically, there are some exceptions, but for the most part, the joint reaction forces, the reason we have to solve for 2 components is that we don't know which direction the joint reaction forces are acting. So we have to solve for each component individually. Okay. Generally, we're going to know the muscle force direction because you can very easily align it with either the muscle fibers or the tendons that attach to the body segment. But the joint reaction forces, typically we don't know the direction. So we have to solve for 2 independent components. Okay. All right, so that's kind of what we started last Wednesday. And so we did a couple of examples on that. We even did an example that's statically indeterminate. So the first thing we're going to do today is just kind of continue on with this and kind of keep going with our examples. Okay. All right, so that's just a kind of a summary of what we went over last time. Are there any questions on any of this? Okay. All right, so let's keep it rolling then. Okay, so let's move up the arm a little bit. So let's look at the shoulder joint. And in particular, let's look at the action of the deltoid muscle. Okay. So the deltoid muscle is a very important muscle on your shoulder. It kind of sits on the very lateral edge of your shoulder. And it's responsible for basically adduction and abduction of your arm. Okay. And so one of the most common ways to work out your deltoid muscles at the gym is to do an exercise called a lateral raise. Okay. And so if you've never seen that exercise before, basically you're standing up straight, or you can do it sitting down too, I guess. And you hold the dumbbell in one hand and you just raise the arm up like this, right? So it's a great way to kind of isolate your deltoid muscles and get
a good workout there. Okay. And so visually, it looks something like this. And so for this, we need to draw the entire arm. So we're going to draw both the upper arm and the lower arm. Okay. All right, so on the right-hand side here, that's the hand. And so typically you're going to be holding a dumbbell. Okay. I know you don't hold a dumbbell like that normally, but it's kind of hard to draw otherwise. So imagine that that's a dumbbell. So we know the weight of that. So that dumbbell is going to be acting with the weight W. That weight is going to be pointing downwards, right? And then your deltoid muscle is going to be acting at the shoulder. So on the very left-hand side of this arrangement here. Okay? So your deltoid muscle kind of, it's kind of like almost like a spherical muscle. And it kind of attaches like right here. Okay? So the fibers kind of run this way, right? And so when the deltoid muscle contracts, it's going to apply a force in that direction right there. Okay? And then the other thing we should draw into this figure is the location of the shoulder joint itself. Okay. So in this configuration, we're going to assume that the elbow joint is locked, and so there's going to be no motion. There's going to be no relative motion between the upper and lower arm. The only the only action that we're going to be looking at is around the shoulder joint. Okay. So this dot right here, this is the shoulder joint. Okay. And so just like we usually are for these problems here, we're interested in solving for. So we're going to compute. Number one, let's compute the amount of muscle force from the deltoids. Okay. And the other thing we're going to compute is the joint reaction forces at the shoulder joint. Okay. And for this problem, we're going to solve for the joint reaction forces, one in the x direction, one in the y direction. All right, it's a pretty standard problem. Actually, it is quite similar to our, to our bicep curl, just, the geometry is just a little bit different. Okay. Okay. So let's state the known quantities, and so let's state the things that we do know. Okay. So one thing we know is that we know the weight of the dumbbell at the end. Okay. Let's assume that we know the length of the arm. Okay. Let's say that we know the weight of the arm. So we're going to concentrate the weight of both the upper arm and the lower arm into the same point. Okay. Okay. And just for force summation purposes, we're going to assume that the weight of the arm is going to be acting at the elbow, right? So we're going to concentrate all that weight into just a single point mass, and that point mass is going to act at the elbow. Okay. Let's see. We also know the moment arm of the muscle. Okay. So that's going to be the distance between distance between the shoulder joint itself and where the deltoid muscle attaches. Okay. And then finally, let's assume that we also know that the attachment angle of the muscle as well. Okay. So we're going to label all these in the free body diagram, but just to be 100% clear, this is everything that we know. Okay. All right. So the next step is going to be our free body diagram. So I'm going to assume I'm going to basically model the entire arm as just a really long stick. Okay. All right. Where on the left-hand side, we have our shoulder joint. On the right-hand side, we have the hand. All right, so let's go ahead and start putting things in here. So first thing we have here is the weight of the dumbbells. Okay, so that's acting at the hand. The other thing that we have is the weight of the arm itself, which remember we're saying we're concentrating it into a single point mass, and that's going to act at the elbow. And so we'll call that WA. Okay. All right. Our unknown in this case is the muscle force. Let's go ahead and include that in. So we're going to say the muscle force acts right here. Okay. We know the attachment angle. So we know, remember, the attachment angle is the angle that the muscle force makes with respect to the body segment. Okay. So that's this angle right here. We'll call that theta M. Okay. And then, of course, we also know all the distances as well. So the distance between the shoulder joint and where the muscle force acts, that's the muscle moment arm. So we'll call that LM. Okay. The distance between the shoulder joint and where the weight of the arm acts, we'll call that L sub A. And the distance between the shoulder joint and the end of the arm where the hand is, we'll call that LW. Answer over there. Okay. And then the last thing that we need to include here are the joint reaction forces. And so these are reaction forces that are acting at the shoulder joint. Okay. So we have a reaction force in the X direction, so we'll call that JX. And we have a reaction force in the Y direction, JY. Okay. All right. Remember, when you're including the joint reaction forces in your free body diagram, it doesn't, the direction or whether you're pointing up or down or left or right, that doesn't really matter all too much. The only thing you just have to remember is that if you just stay consistent with that in your equations. And so when you're summing up the forces and you label JX as going from left to right, which is what we have here, make sure you include it as a positive force. It could be, or it could happen. I don't think it's going to happen in this problem. That when you solve your equations, you may get a negative joint reaction force. Okay, I don't know why I put negative in quotes. There's no, it's actually going to be negative, right? And so if you get a negative joint reaction force, all that means is that the direction is flipped. And so in reality, if you drew it originally pointing up, if you get a negative joint reaction force, that means that the real direction is down. So that's all it means. And so if you get a negative force from your calculations, don't panic. All it just means is that it's in the opposite direction. The only time where you should panic if you get a negative result is that if you get a negative muscle force, right? That's the one that shouldn't be possible, because if you get a negative muscle force, that means you either drew your free body diagram incorrectly, or you have some direction messed up. Because remember, muscles can only apply tension, right? So they can only contract, and so it's impossible for them to push outwards. Okay. So that should be the first thing that you check in every problem. And usually the muscle force is going to be the first thing that you solve for in these problems. And so, if you get a negative muscle force, that means you should either check your equations or check your free body diagram to make sure everything's pointing in the right direction. Okay. All right. So let's go ahead and start solving this problem. So the first thing we're going to do is we're going to sum up all the moments around the shoulder joint. Remember, when we do these problems, we like to start with the moment equation, just because, then it eliminates two of our unknowns from the equations. Because we're summing up the moments at the shoulder joint, that means Jx and Jy are not going to be part of the equation there, and we can solve it directly for Fn. Okay, so if we sum up all the moments, and we're doing it about the shoulder joint, I didn't write Z here, but it's implied that you're summing up the moments, in the Z direction, right? What you get from this is, let's start with the contributions from the weights. Okay. So we have the contribution from WA, so that's going to be minus WA multiplied by LA minus W LW. Okay. So remember the moment equation, we're taking the product of the force as well as its moment arm, and we're applying a sign based on what direction that the force is going to rotate. Okay. Both WA and W here are applying forces that would cause a clockwise rotation, and so that's why we make them negative. Okay. On the other hand, the only other force that's going to contribute to the moment here is going to be the muscle force, Fm. Okay. And based on the figure there, you can see that Fm is going to produce a counterclockwise moment, and so we're going to make it positive. Okay. And so for the contribution from the muscle force, we have Fm multiplied by sine theta m. Remember, when you're considering the muscle force or the moment that comes from the muscle force, you only want to consider the component of the force that's going to contribute to rotation. Okay. I know we discussed this last time, but it's an important point. So let me go ahead and do it one more time. Okay. And so if we look at that part of the figure, right? And so if we have here the shoulder joint, okay, we have Fm that's going like this. Okay. And this right here is theta m. Okay. If we break up that Fm into its two components, right? So we basically draw a triangle. And we have two components like this. And so the vertical component in this case is going to be Fm sine theta. And then the horizontal component is going to be Fm cosine theta. Theta. The reason we only include Fm sine theta is that, Fm sine theta is going to contribute to rotation, right? And so it's acting a certain distance away from the joint. And so that's going to cause it to cause a rotation like this. Okay. Whereas if you look at Fm cosine theta, and you look at kind of where the vector originates and the direction that the vector is pointing, Fm cosine theta points directly at the joint, right? So Fm cosine theta is not going to contribute to any kind of rotation or any moment at all. Okay. Right, and if you ever need a visualization of this, think of any kind of device that has like a hinge joint, right? And so for those of you in the classroom right here, there's this kind of dock cam that's out here, right? And so this dock cam has a hinge joint that kind of acts like this, right? If I applied a force directly at this joint, it's impossible for me to get the dock cam to rotate. It's only if I apply a force that's some distance away, that's the only way to get that to rotate. Okay. So you want to be really careful when you're summing your moment equations. You only include the component of the force that's going to cause rotation. Okay. And of course, we multiply that by the distance, which is LM. Okay. All right. Any questions on this equation here? Okay. All right. And of course, all of this is equal to 0. Okay. So we have our moment equation here, and we have everything that we need to solve for Fm. So let's go ahead and do that. Okay. So I'm going to move both the WA and W terms over to the other side of the equation. Okay. So on the left-hand side, we're left with Fm sine theta m multiplied by Lm. Okay. And this is equal to WA LA plus WLW. And finally, if we want to solve for Fm here, we just have to divide by Lm sine theta m. Okay. And so we do that, we get Fm is equal to WA LA plus WLW divided by Lm sine theta. Okay. So this is actually very, very similar to our result from the from the bicep curve, right? And so that was, I think, the first example that we did last Wednesday. Okay. The only difference in this result here is that we have a sine theta m on the ball. Okay. So this is kind of the point that we ended with last time, but I do want to go over it one more time just because of just because it's kind of an important point. Okay. So this term right here, this term, you can kind of think of it as the effect of the attachment angle on the muscle force. Okay. And so in particular, the way that the attachment angle enters into our result here is that we have to take sine of that angle. Okay. And that angle, theta m, has two kind of extreme values, right? So typically the way theta m is measured, or the attachment angle, it's some kind of acute angle. So it's anywhere between 0 degrees and 90 degrees. Okay. So let's look at kind of these two extremes. Okay. And so let's think about what happens to sine of theta when as theta goes from 0 to 90. Okay. So let's look at 0 first. And so what is sine of 0? Sine of 0 is just 0, right? Okay. What happens if you had an attachment angle of 0 degrees in this result, right? Yeah, so if you had sine of 0 degrees on the denominator there, we'd have Lm multiplied by 0. And so that's going to give us 0, right? And so if we have Fm is equal to WALA plus WLW all over 0, then that means the muscle force is undefined. Okay? There's almost never a situation in your body where the attachment angle is 0, but there may be some cases where the attachment angle is very parallel to the bone itself, right? So you may get attachment angles of maybe like 5%, 10%, 15%. Okay. And so in general, when the attachment angle goes lower, that increases the amount of muscle force that's required to hold a certain position. And so the other extreme for theta m here is 90 degrees. And so sine of 90 degrees is 1. Okay. So that's kind of the maximum value that sine of theta can have, right? And so if you think of this, the graph of sine of theta, right, it kind of fluctuates between -1 and 1. But if we're only considering the section of between 0 degrees and 90 degrees, or if you want to do it in terms of radians, it's between 0 and pi over 2, okay? Then sine of theta is only going to fluctuate between 0 and 1. So 1 is really the max. And so when theta is equal to 90 degrees, that decreases the required muscle force, or it puts it at the minimum most value. Okay. And that's kind of what we did with the bicep curl example, right? And so in that example, we assumed that the attachment angle was 90 degrees. And so what we had from that example was the minimum amount of muscle force required to pull off that position. Okay. And then as that attachment angle gets kind of smaller and smaller, it's going to require a greater amount of muscle force to hold that position otherwise. All right. So attachment angle is a very important parameter. And so, depending on what the attachment angle is, it's going to determine how much work or how much force your muscles have to go. All right. Any questions on this? Okay. The interesting thing about attachment angle is that it's not a fixed quantity. In fact, there are different, depending on what position your other body parts are in, the attachment angle can actually vary. It's different than moment arm. So the thing with moment arm, or the attachment distance, that's what we call that. That's pretty much fixed in your body, right? Your tendons don't really move around; they don't detach and attach somewhere else. So LM is mostly fixed. Once you're kind of born with it, and once you kind of grow into it, during adolescence it may change because your bones themselves are getting longer. But once you kind of reach a point in your life where you're not really growing any longer, moment arms are basically fixed. But attachment angles can change. And so depending on the position of your body, some actions may be easier to do than others. Part of that has to do with kind of how the muscles are arranged and what muscles are acting. That certainly plays a role too. But sometimes these differences can just be purely just on when your body's in certain positions, the attachment angle is more beneficial than others. Okay. Okay. So let's do an example to kind of illustrate this. So actually, it's not a whole new example. It's the same example that we just did, but we're going to do it at a slightly different rotation. Okay? So again, we're going to look at the deltoid muscle during a lateral raise. But this time we're going to do it, when the arm is slightly adducted. Okay. So in other words, the arm is going to be pointed towards the ground a little bit, as opposed to being parallel to the ground itself. Okay. All right. So once again, we have our shoulder joint up here. Okay. We have our upper arm. That's our elbow joint. And then we have our lower arm like that. Okay. Once again, at the end of the arm right here, we're going to be holding a weight. Okay. So that's the dumbbell, again, held very inappropriately by this person, but that's okay. And so at the end, we're going to have our weight here. We have the weight of the arm itself. Okay. And of course, the big difference here is the fact that our arm is rotated down. Okay. The way that we're going to quantify that is if I drew kind of an imaginary vertical line at the shoulder. Okay. I'm going to characterize this angle right here. So this angle is going to be theta A. All right. And so we need our muscle force again. And so we're going to assume that our muscle force is going to be like this. Okay. And then because our arm is in a slightly different position, we're going to say that the muscle, the attachment angle here is going to be different as well. Okay. So this angle right here, right? Previously, we called that angle theta m. And so let's say that now this angle is theta m2. We're going to leave it vague right now. We're not going to say it's bigger or smaller. And so we're going to work through this problem and we're going to compare our results to the previous problem. And we're going to see, you know, whether a bigger angle or a smaller angle actually helps. Okay. Okay. But all the rest of the knowns are going to be the same here. And so, you know, once again, we're going to compute. Let's compute the deltoid muscle force. And then let's also compute the joint reaction forces. All of the known variables are the same. So once again, we know all the weights that are acting. We know the length of the arms. And the only new known quantity here is the angle of rotation of the arm itself. Okay, so it's going to be theta A. But everything else is going to be the same. So I'm not going to repeat here. Okay. All right. Any questions on just the setup of this problem here? Okay. All right. So let's go. Let's get to solving it. So let's go ahead and start with our free body diagram. Okay. So free body diagram, once again, we have our weight here, W. We have WA. Okay. We have these lengths, and so the length from the shoulder itself all the way down to the end. This is LW. The length from here to the elbow, we'll call it LA. Okay. And then we also have the muscle moment arm, that's LM. Okay. Okay. We have the muscle force FM, that's acting right there. And then we have theta M2. Now you have to be careful here, right? And so this is kind of relevant for problem 3A on the homework. Usually when I give you an attachment angle like this, a muscle attachment angle, it's always measured relative to the body segment. Okay, so this theta M2, this is the relative angle between the muscle force vector and the bone that it's attached to, which is the upper arm bone, the humerus. Okay. It's important to know that this angle here is not relative to the horizontal axis. Okay? I think a lot of times, when you're given an angle, you assume that that angle is relative to the x-axis. This time, the angle is actually relative to the bone itself. And so that's going to affect your calculations. And so maybe it may not come into play for your moment equation, but when you do the sum of the forces in the x direction and the y direction, that's going to affect your results. Okay. Okay. And then before we actually start making force equations, we also have a force in the x direction, so we'll call that Jx, and then a force in the y direction, Jy. Okay. Okay. So the last thing I want to add here, before we jump into the the force equations, okay, we have to incorporate this theta A right here as well, okay, because that's definitely going to affect our calculations. It's a little bit busy on the left-hand side there. We can have a lot of quantities there, so I don't want to make that any more busy. Okay, but due to the parallel line theorem, okay, we know that angle, right? So the shoulder angle, you can call it the armpit angle. It's basically the angle of your armpit. Okay, so the armpit angle. Another place that we can put it in this figure is right there. Okay. So that's going to play a pretty important role. Okay. Okay. All right, so let's go ahead and start solving this, right? So our unknowns in this case are Fm, Jx, and Jy. Just to kind of, I know normally we start with the moment equation. Actually, let's just start with the moment equation, and then we'll come back to the force equations after that. Actually, I realized we didn't do the force equations on the last example, but we'll do it here. All right, so let's solve the moments around the shoulder. Okay. All right, just like we did with the with the previous example, let's start with the weights. Okay. Now you have to be careful here, right? And so when you're computing moments, right, the moment arm that you compute should be the perpendicular distance between that vector and the joint itself. Okay. And so, if you're looking at this problem and you're seeing that it's very similar to the previous one, you may be tempted to say that, the moment contribution from the dumbbell is just going to be W, LW. Okay. But you would only be part of the way there, right? Because if we draw this out, okay, let me go ahead and draw this right here. Okay. Right, and we know this distance right here is LW. Okay. So because the force vector that we're considering here is vertical, okay, what we actually want for this moment arm, okay, this moment arm here is what I like to call kind of the perpendicular distance between the force vector and the rotation joint. Okay. So what that means is that when you want to compute a contribution to a moment, you want to draw a line that's perpendicular to the force vector itself. Okay. Now you want to draw it perpendicular to the force vector, and you want to draw it towards the joint that you're looking at. And so for this particular case, you know, our force vector is vertical here, okay? And so we're going to draw a line that's perpendicular to that. Okay? Let me go ahead and draw this line like that. Okay. So you can see that that angle right there is perpendicular. Okay. Once that perpendicular line crosses the plane where the joint is, right? It's going to use a different color for that. And so this red line here represents the joint itself, but I'm just kind of extending it downwards towards that line. Okay. Once that perpendicular line crosses the joint itself, right? That's the distance that you want to incorporate into your moment equation. Okay? So this distance right here okay, so this distance, this is what you want to incorporate into your moment equation. Okay. All right. And so you can just kind of tell from the figure here that that distance isn't LW. Okay. Okay. And so you know, if you kind of look at the triangle here and remembering that we also know the armpit angle. Okay. So the armpit angle in this case is theta A. Okay. And so if you use trigonometry, that distance that we want, right? Knowing that the angle right here is theta A, knowing that the hypotenuse of this triangle is LW, okay, that distance right there is going to be LW multiplied by sine theta A. Okay. So that's what you're going to incorporate into your moment equation. Okay. All right, so we can use the same logic for the weight of the arm itself, right? So the weight of the arm very similar. It's also a vertical force that's pointing downwards, except the hypotenuse of that triangle is LA, not LW. Okay? And so if we apply that same logic to the weight of the arm, we're gonna have minus WA times LA, okay, sine of theta A. Okay, so those are the two contributions to the moment from the two weights. Okay, so they're adjusted now because of the angle of the arm. Okay? And now we have the contribution from the muscle force itself. Okay? But before I do that, are there any questions on these two contributions here? Okay. All right, let's get to the muscle force then, because I think this is kind of a big point of confusion for you know, for this homework. Okay, so let's go ahead and draw. I'm just going to draw the upper arm just like that. Okay. And then the muscle force is coming in like this, right? So that's FM. And then we know the attachment angle. The attachment angle is theta M2. And we know the joint. The joint is right here. We know this distance right here, which is LM. Okay. I know the way that I drew it here, it kind of looks like FM is pointed vertically upwards. It might be. It depends on the values of theta M. But you know, we don't know if FM is pointed vertically upwards. Okay. We know the W's were pointed vertically down because those are gravity forces, those are weights. And we know gravity always points straight to the ground. Okay. So we don't know exactly what direction FM is pointing pointing in this case. The only thing we know is that it's measured relative to, theta M here is measured relative to the arm itself. Okay. And remember that we have this angle right here, theta A. Okay. Okay. So what we want to do is we want to compute, or we want to find out what is the contribution from FM to the moment around the shoulder joint. Okay. So for these situations, where we don't exactly know kind of the direction, I'm gonna start kind of the same way we did the last one, where I'm gonna break up FM into its two components. Okay. Okay. And so using theta M2, right? And so this will be a little bit hard to visualize because the entire thing is slanted, right? But I'm gonna do a component that's perpendicular to the arm, okay? And then a component that's parallel to the, okay? Only using theta M2 here. Okay. So the component that's perpendicular to the arm, just like in the last problem, that's going to be FM sine of theta M2. Okay. And then the component that's parallel to the arm, that's going to be FM cosine of theta M2. Okay. So I'm not even considering theta A at this point. I'm doing it just purely based on the muscle attachment. Okay. Okay. So the reason I'm doing this is that you kind of clearly see here that only one component of this force here is going to contribute to rotation, right? Because what do we know from the previous problem? If you have a force component that's pointed directly at the joint, we know that that contribution, that's not going to contribute to any moment at all because it's not going to cause any rotation. Okay, so we know off the bat that this component here, Fm cosine of theta m2, this is not going to contribute to the moment. And so the only contribution to the moment is going to be from Fm cosine, Fm sine of theta m2. So let's start with that. Okay. Okay. So now that we know, which component of this force is going to contribute to the moment, right? Let's compute its moment. So just like we did up here, right? Let's take a line. Let's take a line that's perpendicular to that force vector, and then let's point it towards the joint itself. Okay. And so let me go ahead and let me erase some of this just to make it a bit cleaner. Okay, so I'm looking at just that vector Fm sine of theta m2, right? And so we're going to draw a line that's perpendicular to this. Okay. So we know that purple line is perpendicular to that force vector, and we're going to point it towards the joint itself. Okay. And then eventually, we reach this part right here where we kind of cross the point of where that joint is. All right. And so what we need to multiply by this force is that distance in purple right there, right? But if you look at this figure, right, we actually already have that purple distance already quantified. And so that is already Lm. And so in this case, we don't need to do any additional trigonometry here. We can just multiply this force by Lm. Because that Lm right there, that's exactly the perpendicular distance we need between Fm sine of theta m2 and the shoulder. Okay. All right. So if you notice here, when I'm considering just the contribution of the moment from just the muscle force, the armpit angle doesn't come into effect at all, right? It's just the muscle attachment. Right? And so if we bring that back up here, right? Oh, and we also know that this is positive because it's going to produce a counterclockwise moment. Okay? And so if we bring that back up here, right, then we have FM sine theta m2 multiplied by LM. Okay? And then this entire thing is going to be equal to 0. Okay. Okay, so that right there is our moment equation. Okay. All right, any questions on how we got that equation right there? All right, so from here, it's just algebra. So we have everything in this equation here. So we know the weights, we know all the lengths, we know the armpit angle, theta m, we know LM, and we know theta m2. So the only unknown here is FM. So let's go ahead and solve this equation for that. Okay. And so once again, I'm going to move all the weight terms to the other side. And so that's going to give us FM sine of theta m2 times LM is equal to W LW sine of theta A plus WA LA sine of theta A. Okay. Let's divide this by LM sine theta M2. Okay. Another thing I'm going to do, just so that we compare this to the previous answer, is that I noticed that both of these terms have sine theta A, so I'm going to factor that out of the equation. Okay. And so we have FM is equal to, okay. I'm going to do it like this. I'm going to put both the sine terms outside. So we have sine theta A divided by sine theta M2, okay, multiplied by quantity WLW plus WALA divided by LM. All right, so that's the muscle force, when the angle is different. Okay, so let's compare this result to our previous one when the arm was perfectly extended. And so we call this FM2. So this is kind of the muscle force in kind of the second configuration, right? What I'm going to do is I'm going to take the ratio. So I'm going to take the ratio between FM1, which is the muscle force when the arm is perfectly adducted or abducted, excuse me. Okay. So that's FM1 divided by FM2. Okay. So this ratio that I'm computing here is the ratio of the deltoid force in the previous example to this one. Okay. And so just for the sake of time, just because I do want to finish all the upper extremities today, I'm just going to give you the result, okay? Basically, what's going to happen is that everything in the parentheses here, okay, that's going to cancel with each other because that's basically identical to the last one. And so the only factors that you're going to have here are going to be just from the difference in the angles. Okay. Okay. And so if you do that, what you're going to get is sine of theta m2 divided by sine of theta m1 multiplied by sine of theta a. All right, question in the chat. All right, question in the chat. Am I planning to give some sort of study guide before the exams? Should we focus more on the kinematics rather than the definitions? Yes, so I do. I always give a study guide before the exams. So the study guides are basically just a summary of all the learning objectives that we've covered, in this unit so far. So that's going to cover all the conceptual knowledge I expect you to know. And then for the problems themselves, I always tell people just to study the homeworks. So the homework problems I usually give are usually kind of usually a step up in difficulty. And then for the exams, because the exams are kind of a shorter, you have a much less time on the exam, I'll usually give you a little bit of an easier problem on the exam compared to the homeworks. Yeah, but I will be providing a study guide. Usually I provide it a little bit like a week and a half before the exam. Yeah. Mm-hmm. Yep. All right, and so you can kind of plug numbers in here, and you can kind of see, okay. But I will say that generally speaking, theta m2, okay, basically as your arm kind of gets closer and closer to your side, right? Theta m2 is generally less than theta m1. Okay. So kind of the best case scenario for your deltoid is kind of when it's kind of fully out here like that. All right. Any questions on this? Okay. So I don't have this in the notes, but it is important to know. Let's do one of the force summations too. Okay. Because I want to give you an example of how to factor in multiple angles into a force computation. Let's do y direction. Okay. So this is going to be a bit different than the previous examples because we have kind of multiple angles to kind of take into account here. Okay. In particular, the one force that's going to have an interesting kind of direction here is going to be the muscle force. Okay. Okay. So in the previous moment equation, when we did the contribution of the muscle force to the moment, we didn't have to consider theta A, just because, that theta M was measured relative to the arm itself. But now we're summing up the forces in the perfectly vertical direction, okay? And so the fact that theta, I guess technically it's theta M2, right? The fact that theta M2 is not measured relative to the horizontal, that means it's going to make it a little bit more difficult to account for that, okay? Okay, so let's go ahead and sum the forces in the y direction. Okay. All right, so let's start with the easy ones. And so actually, let me scroll back up to the free body diagram just so you can see. Okay. Okay, so here's our free body diagram. We have 5 forces here. So we have Jx, Jy. Those are the joint reaction forces. We have W, Wa. Those are the external weights. And then we have Fm as well, right? If we're summing up the forces in the y direction, we know right away that Jx is not going to factor into that equation because Jx is a horizontal force, okay? And so we basically have 4 contributions to the y equation, okay? We know right away that W, Wa, and Jy, those are going to be easy to account for just because those are pointed perfectly upward. So let's start with that. Okay? So if we sum up the forces in the y direction, we know we're going to have a positive Jy. We're gonna have a minus WA and a minus W, okay? So those are all the perfectly vertical forces, and I've included their signs depending on whether they're pointing up or down. Okay. But now let's look at FM. Okay. And so just based on the figure, we know that FM is going to be a positive contribution, right? We can kind of tell already that it's going to be pointing upwards, but it's going to have some kind of trigonometric modifier there. Okay. So once again, let me go ahead and draw. And I'll draw it a little bit bigger this time. Okay. So we know that FM is acting in that direction there. So we know it's not perfectly vertically upwards, but it is close to vertical. Okay. And then the two angles that we're given here are theta M2. Okay. And we know that theta A is right here. Okay. Okay. So what we want, right? What we want to plug into this equation is we want to compute the vertical component of FM, right? So the component of FM that points vertically upwards. Okay. And so what we're given, right? We're given the direction of FM, but we're given it in kind of a roundabout way because we're given it in terms of all these different angles here. Okay. So kind of the challenge here is, how do we use these angles? How do we use theta A and theta M2 in order to get the component of F in that direction? Okay. Okay. So there are a lot of different ways that you can do this. And so, as we kind of do these problems in the class, I'm going to try. I personally, I don't have like a favorite method or favorite way of doing this. Because sometimes depending on the problem, some methods are more convenient than others. When I do examples in the class, I'm going to do my best to kind of give you different looks, and so different situations where you can use one technique over another. Okay. But one thing is pretty consistent is that you should always look and see where your reference axis is. Okay. So you should look. So I always say the first thing that you should look for in these problems, where the trig can get pretty complicated in these problems. You should look for an angle that's measured relative to one of the principal axes, either the horizontal axis or the vertical axis. Okay. Okay. All right, so we have two angles here, right? So we have theta A and we have theta M2. Okay. Let's describe what those two angles are measuring in kind of in words. Okay. So let's start with theta M2. Okay. So theta M2 measures the angle between the force vector and the direct and the upper arm. Okay. Okay. Whereas if we look at the definition for theta A, okay, theta A measures the angle between the upper arm and a vertical line. Okay. And so between those two angles, right? So between theta M2 and theta A, which angle here is the one that's measured relative to a principal axis? It's theta A, right? So because theta A is the angle between the upper arm and a vertical line is basically the same thing as the y-axis. So let's start there. Okay. Okay, and so if we were to just look at theta A, right? And so if we draw a vector that goes in the upper arm direction, right? So if we draw an angle or a vector that looks like this, okay? Right? If we were to take just theta A in that vector, you know, how would we do that based on trigonometry, right? And so if we call this vector V, right? And so if we wanted the component that's just in the y direction, we would take V, right? And so we basically draw a right triangle that kind of looks like this. Okay. Where this is kind of a right angle right here. Okay. Right. Sorry, I drew that kind of weird. This is the right angle that we want right here. There we go. Okay. Trig is always kind of screwy, right? So you in your mind, it's like, oh, it's just trig. You know, I did that years ago, but you know, it can really mess with your head if you don't draw the lines correctly. Okay. Okay. And so if we want the vertical component of this, right? Right. So the way we're gonna do that, we're gonna use cosine, right? So we're gonna take V cosine theta A, right? Okay, good. All right, but that's not the vector that we want, right? The vector that we want is Fn, right? So here's kind of a technique that I like to do, right? And so if you look at these descriptions here, right? Right, let's start with theta A. Ultimately, what we want is we want an angle between, you know, Fm and the vertical axis, right? So you know that theta A here is the angle between the vertical axis and the upper arm, right? Whereas theta M2 is the angle between the upper arm and Fm, right? And so just by chain rule, well, not actual chain rule, but you know, the chain rule that transitive property, that's the one I was looking for, right? The thing that both of these angles have in common is that they're both relative measuring angle relative to an upper arm, right? So what this tells us, right, is that we can either add or subtract these two angles in order to get the angle between Fm and the vertical axis. Okay? Sometimes you're going to add angles together, sometimes you're going to subtract. Okay? But the fact that both of these angles here have that upper arm in common means that we can actually relate them to each other. Okay. Okay. So how are we going to do that? So I like to think of this kind of in a very kind of visual way, right? I'm a very kind of visual person myself. Let's look at theta A, right? So the way I like to think about this is, you know, how do we actually get from, you know, theta A to a certain, you know, or what direction is theta A actually rotating in, right? And so from this perspective right here, right, we can see that in order to go, right, from the vertical axis down to the V vector, right, let me actually use a different color so you can see. Right? So one way that you can think of angles is that angles kind of represent a rotation of a vector, right? So you start from a certain direction and then you rotate into a different position, right? And so in order to rotate from the vertical axis down to V, we have to rotate counterclockwise by an amount theta A. Okay. Okay. Okay, so that's to get from the direction of the vertical axis to the upper arm. Now let's look at theta M2, right? So if we start from the upper arm, right? and then we go into the direction to FM, right? And if we think of theta M2 as kind of a rotation from the upper arm to FM, right? We have to do a clockwise rotation of theta M2. Okay. All right, so because both of these rotations are in opposite directions, what that means is that we should actually subtract these angles. Okay. Okay. So if the angles show opposite rotation, you're going to subtract. Okay. Okay, so the modifier here, so we already know the modifier is cosine, right? So we've already established that we want to take a cosine of the angle. The only thing that we have to establish now is what cosine of what angle that we want to do. Okay? And so because these two angles are in opposite directions, okay, the trigonometric modifier here is going to be cosine theta A minus theta M2. Okay? And of course, this is multiplied by Fn. So that right there, that's the vertical component of Fm2. And so that's what you would plug into the Fy equation, right? So this method that I just showed you of kind of visualizing the rotations and doing kind of the transitive properties of angles. I don't know if this is actually kind of a scientific way of doing this. This is just kind of my own way of thinking about it after thinking about these problems for 12 years of my life. So this is kind of just what I've come up with, but so this to me kind of makes the most sense. It's a visual way of thinking about it. But if you have kind of other ways to kind of think about these angles, then whatever works for you. Okay. The good news about this is that this is not the only way to express this. You can also express it in terms of sines of certain angles. But to me, this is kind of what makes the most sense. Okay. All right. Any questions on this before we wrap it up for today? Okay. All right. So that's all we got time for today. So unfortunately, I didn't get a chance to talk about upper extremity injuries. So we'll talk about that first thing on Wednesday. And then we'll move on to lower extremity biomechanics. So thank you guys for coming today. Hope you guys have a good rest of your day, and I will see you guys on Wednesday.